This is going to be a video on gyroscopic precession, spin drift, Magnus effect. I think these are all interesting subjects, and what makes them more interesting is if somebody doesn't know anything about these subjects and they were to watch videos that explain them, they still won't understand them after they watch the videos. So I'm going to explain this on a very simple level that I think anybody can understand. The Magnus effect part is what I just figured out on my own, and it's all logic. But then when I get into the spin drift from like a football or a bullet, that's the stuff I picked up from experts, from checking several different sources, and I'll explain that. Okay, so first off, I'm going to explain Magnus effect. The way that Magnus effect is typically explained is if you have a ball traveling and it has a clockwise spin as we look down on it, and this ball is traveling through the air straight ahead, it will have a relative wind blowing against it. And when I say relative wind, I mean that if you're standing out on a soccer field, you're not going to feel the wind, but as the ball travels through the wind, it'll feel it. So it's a relative wind. Okay, so the way this is normally explained is as this ball travels through the wind and it is spinning to the right, the side of the ball that is spinning with the relative wind will have air molecules that are traveling faster. And why are they traveling faster? They just are. And the air molecules on this side of the ball, since they're traveling faster, they will also be less dense. And why will they be less dense? They just are. So that means you're going to have more dense air on the left side, and that will cause a deviation to the right, and that is the Magnus effect. Sometimes somebody will throw in something like Bernoulli's principle, but that actually doesn't explain anything. That's just the law that states that if something's traveling faster, if air molecules are traveling faster, they will be less dense. So that still doesn't provide an explanation. So I'm going to provide an explanation that is very clear and simple, I think. And by the way, this part right here is just the stuff that I figured out. And I'm no expert. I just like looking into this for fun, and I got tired of watching videos that didn't really explain anything. Okay, so let's take our same soccer ball. I'm going to give it a rough texture all the way around. Let's spin this soccer ball clockwise as it travels forwards through a relative wind. Now the rough surface here on this soccer ball is going to collide with air molecules more violently or with more energy compared to the side that is traveling with the relative wind. You can imagine if you go up to a soccer ball that's sitting on a field and you kick that soccer ball, but instead of having your toes pointed toward the center of the soccer ball, you're pointing your toes obliquely or to the side of the soccer ball. That's going to cause that ball to do two things. First off, it's going to cause it to spin in the direction that you kicked it, and it's going to cause that ball to deflect in the direction that you kicked it. So these air molecules are doing the same thing as your foot. As this ball spins really fast, it's going to collide more violently with the air molecules on this side of the ball as it travels into a relative wind. Those air molecules are going to want to spin the ball in the opposite direction, which will slow the rotation of the ball, and it will want to deflect the ball to the right. But since the ball is already moving forward very fast, it's not going to get deviated to the right downwards. It's going to be deviated to the right as it travels forwards. And that's it. That's Magnus effect. It's actually that simple, I think. And also I'm thinking as for the original definitions I often see on Magnus effect, or the typical explanations about the air traveling faster on one side than the other, I'm thinking since this ball is spinning as it travels forward in a linear direction, the side that is traveling into the relative wind will be colliding with all these air molecules, and they'll be bunching up here, and you'll have a higher density simply because they're all running into each other. But on the side here traveling with the relative wind, the surface of that ball is going to simply pass right through the relative wind because, say, it's traveling at the same speed, so thus the air molecules on this side will be traveling faster and have less density because they're not being all bunched up by colliding with the ball. I was wondering about the ideal spin ratio for the Magnus effect, and here's what I think from this logic. Imagine you have this soccer ball right here, and you kick it so that the side of the ball that's traveling with the relative wind is actually at the same velocity as the relative wind. So that means there's going to be very few air molecules collisions on this side because this side of the ball is traveling with the wind. I just drew a couple of arrows here showing that the surface of this ball will just kind of pass right through that wind. But on the opposite side that's traveling into the relative wind, it's going to have more active or more energetic collisions, so that's what's going to push it to the right. So basically you want to have an object that's traveling as fast as possible to get as much relative wind as possible, and you want the surface velocity, you want it to rotate so that the surface velocity will be the same as the relative wind. So that's my guess. And I'm also thinking that maybe more might not be better, because I'm thinking, say this ball, what if it's spinning at 1,000 RPMs, but it's only traveling at 20 or 30 miles per hour in a straight direction? You're going to have slightly more energetic collisions with air molecules on this side of the ball that's traveling into the relative wind. But relatively speaking, this ball is going to have energetic collisions with air molecules on all sides of it because it's rotating so fast and it's not traveling very fast in a linear direction. So I'm thinking you may not get as much Magnus effect or drift. Don't know for sure. Now let's see how this can apply to cylinders or projectiles such as American footballs or plastic cups or bullets. So first off, if you have a bullet coming right towards you here, here's the center of the bullet. If this nose of the bullet is pointing directly straight ahead right at you, it will have a symmetric relative wind in all directions, so it will not have any deviation from a Magnus effect. Since the wind is hitting it equally on all sides, there's simply no reason for this bullet to deviate one way or another. But now if you take something lightweight, like say a red Solo cup, and you're able to throw it and give it a really hard spin to the right, the cup is so light that when you throw it up, that nose will be pointed up, and as that cup travels over the apex of the parabola and starts to come down, the nose will remain pointed up in its original orientation. This means as the cup falls, it will encounter a relative wind pushing up on it. And most importantly, that wind is pushing up on the side of the cup. It's not pushing directly into the nose of the cup. So here's the back of the cup right here. It's falling, so it has a relative wind pushing up on it. As it twists, this part of the cup that's twisting into the wind will receive more energetic collisions, and it'll want to push it to the left. So if you're throwing something lightweight where the nose stays pointed upwards in the original orientation, you will get a left drift or a left spin drift from the Magnus effect, and it will be significant. Here's a picture right here showing too. I just said that the Magnus will have a large effect on the spin drift. If there's a person on a soccer field here or a pole or whatever, you can kick the ball and actually have the ball twist around from the Magnus effect, and it will be very noticeable. On the next scene, I'm going to show what happens when I throw a red Solo cup with a right spin. Notice as the cup travels upwards, its nose remains pointed up so it doesn't have any drift, but once the cup falls, it encounters that relative wind pushing up on it, and then at that point it starts to deviate to the left. I think that throw looked okay. I think you could see it was traveling in a straight line until the apex, and then it started drifting left upon descent. And on the next page, I'm going to show the spin drift from the gyroscopic precession. So the spin drift I just showed from the Magnus effect, I haven't heard anybody actually call that a spin drift, but the cup is definitely drifting because it is spinning, so it is a spin drift. But when most people say spin drift, they're talking about a gyroscopic precession that happens with heavier objects where the nose will end up pointing down when it descends instead of the nose staying up in its original orientation. So here's how you get the gyroscopic precession. I'll cover this first and then I'll go into spin drift. If you have a ball or an object traveling forwards, you push up on it right here. It's not going to magically jump up to a higher point. It's going to take off at an angle right there. So now you put this weight or a ball on a ring that's spinning, and you can just imagine a ring as having several separate weights attached to it. The ring is spinning right here, I guess you'd say counterclockwise as you look down on it. If you push up on this section right here where this weight is, then this weight is going to travel up to the right, just like right here. So you get a tilt in your ring at 90 degrees from where you pushed it up. This is what causes the gyroscopic precession of a bicycle wheel. If you have a wheel hung from the ceiling, from like a rope, and you spin this wheel really fast, and say this wheel right here, for example, is spinning, the top of the wheel is spinning towards us. It's kind of tough to show that here in 2 dimensions. So this bicycle wheel has the top of it spinning towards us. Gravity is pulling the top of this wheel down, or this top weight down. And just like the same effect, where if you push up on a ball, it's going to go up at an angle. So now as this weight comes around here, it's actually going to be pushed that direction, and it will cause the bicycle wheel to spin, or sorry, to precess in the opposite direction that it's spinning. So in other words, the bottom of the wheel here is traveling away from us, which means the wheel should be coming towards us. But because of the gyroscopic precession, the wheel will actually travel away from us. Okay, so that's gyroscopic precession. Now I'm going to show how that can cause spin drift. And by the way, what I'm going to show here, this wasn't stuff I figured out from my own logic. Everything I'm going to show here is more of an amalgamation of different bits and pieces that I picked up from separate Google sites and videos and whatnot. Okay, so let's say that a bullet travels through a gun. The barrel of the rifle will be rifled in what they call a right-handed twist. So as you look down the breech of the rifle towards the front of the barrel, you will see a clockwise twist. And we're looking at the back of the bullet right here, or the back of a football. So if you're going to shoot at something from a distance or throw the football at something at a distance, the point will be pointed up right here initially. The bullet will travel up, travel along a parabolic path. But because the bullet is traveling much faster and it is heavier, you're going to get a wind vaning effect, where as it travels into the wind, that wind is going to push the back of the bullet equally so that the nose will stay pointed in the direction of flight. So as that bullet travels over the parabolic path and comes back down, the nose will continue to be pointed forwards instead of being pointed up, like with the red Solo Cup. Now as this bullet, the nose of the bullet gets pushed down like this, and encounters an upward relative wind on it pushing right here, from what the experts say. And it's because of this relative wind, upward wind on the nose, as the nose begins to point down more and more, that upward wind is what causes the gyroscopic precession, which causes the spin drift, and I'll explain that. Here we're looking at the back of the bullet that is spinning clockwise. The nose of the bullet will be pointed up from the wind, as I just showed, which means this position number 1 here on the back of the bullet will be pointed towards us. But because of gyroscopic precession, since the top here is receiving a force that's going to point this ring towards us, that means that at point number 2 right here is the part that will actually be pointed towards us. And if the top part of the bullet will be pointed towards us because of the wind lifting the nose up, then that means the bottom part will be pointed away from us. And as this bullet travels around, that means you're actually going to get position number 4 here pointing away from us, going into the page. So the bullet will point towards the right, and you will get a rightward deviation, or a right spin drift, that again is relatively slight at only a few inches at about 800 or 1,000 yards. So Magnus effect will cause a left spin drift when the nose is pointed up, typically on a lighter object that's moving slower, from what I understand. And gyroscopic precession will cause a right spin drift on an object that's moving faster or that's heavier, and the nose stays pointed in the direction of travel. Just for another interesting point, on the next page I'm going to show how fast a bullet spins. From what I've read, most rifles in America have a right-handed twist, but when you go to other countries, you may encounter more left-handed twists, or left-handed rifling of the barrel. So a right-handed twist in the rifling of the barrel means that if you're looking down the breech of the rifle towards the front of the barrel, you will see a clockwise twist. And a typical twist would be, it's measured as twist per inches, so it's 1 twist per 8 inches. Let's take that 8 inches, do some conversion equations, 12 inches per foot. The average velocity of some of these long-range rifles, like the 30-06, is about 2,500 feet per second. And so if inch divided by inch cancels, foot divided by foot cancels, we're left with seconds. 2.66 repeating times 10 to the negative 4th seconds. That is how long it takes for the bullet to travel those 8 inches. And those 8 inches is what causes 1 revolution of the bullet. So now we have 1 twist, or 1 revolution, every 2.66 times 10 to the negative 4th seconds. With fractions, you can multiply or divide your numerator or denominator by whatever you want, but you have to do the same to both sides. So in this case, we don't want 2.66 times 10 to the negative 4th seconds in the denominator. We just want 1 in the denominator. So the way we turn this number into a 1 is we divide it by itself, and that becomes 1 in the denominator. So we end up with 1 second, but that also means we have to divide the numerator by that same number. And this is just the long way of saying that you take 1 divided by 2.66 times 10 to the negative 4th seconds, or you simply take 1 divided by your denominator, and you're going to get 3,750 revolutions per second, which is an extremely fast spin rate. Think about how short a second is, and know that that bullet is traveling 3,750 times in that 1 second. And I'm going to assume that the bullet doesn't skip over any of that rifling, because if it did, then there's no reason to have such a tight spiral. You might as well relax out that spiral and make the bullet twist slower. So at 3,750 revolutions per second, 60 seconds to a minute, that is 225,000 revolutions per minute, or RPMs, and that is an extremely fast spin rate. So I think that's interesting. But again, from everything that I've seen, even though this is an extremely fast spin rate, you're not going to get any Magnus effect on the bullet, because the nose of the bullet stays pointed in the direction of travel, unlike the red Solo Cup, that the nose remained pointed up in its original position as it descended. By the way, I did tape a small rock to the tip of that red Solo Cup to try to get the nose to come down for a wind vaning effect, but that didn't work. So I used something heavier. I actually took a socket from a wrench, and that socket was pretty heavy, and I taped it to the front, and then I got the nose to point down, so I got the wind vaning effect when I threw the cup with that same right-handed twist. But at that point I had no leftward deviation, so there really wasn't much to film there. It just went up in the air and came right back down. But I imagine if I were able to throw that cup, I don't know, 50 or 80 or 100 yards or so, like a football, then I may get a little bit of a right deviation from spin drift. So that's it. I think that's actually extremely interesting. You throw 2 separate objects in the air. One object will deviate to the left from Magnus effect. Another object will deviate to the right from gyroscopic precession. And it all depends on which way the nose is pointed when it's falling. So again, yeah, I just think that's super interesting.